All right, so before we officially start Mod 3, I wanted to go over the structure of Mod 3 and what that looks like. So I would kind of separate Mod 3 into two parts. One, we're sort of like tying up the loose ends from the last mod in the first half. And then the later half is just all new algorithms. So with sections 22, 23, and 24, these are all sort of tying up the loose ends. So linear algebra and calculus math concepts that were actually used in linear regression, but we didn't really talk about them. I think oftentimes it's a little bit overwhelming to like get really into the math of things, especially that, you know, we're also coding at the same time. So we're going to actually backtrack a little bit, and today we're actually going to see where linear regression, where linear algebra comes into linear regression. So we're going to take a look at that, and very similar to section 23, we're going to talk about calculus. We're going to talk about how gradient descent works. So one, it ties up the loose ends of what we were doing last mod with regression, but also a good jumping off point for the rest of the material, because all of the algorithms that we're going to talk about for the rest of the mod are algorithms that make use of both linear algebra and calculus. I will preface by saying it's not absolutely important that you understand all the math that goes on behind algorithms. As we go through it, I'll explain how much you do need to know. But it's good to be able to, you know, I think if you're really serious about machine learning, good idea to familiarize yourself with some of like the concepts, of which I will go through as we move through the mod. So as I mentioned, 23, 22 through 24, and regularization, as you can see, these are actually more regressions. And these are regressions that actually may or may not help with your last project. So with 24, we're going to go back to that. And then from 25 onwards, every section pretty much is a new algorithm. And so linear regression was one algorithm. Each one of these sections is going to be a new algorithm. So it's going to be a little bit intense. We're going to be meeting new algorithms every study group. But what I will say, the way that those are coded out, all the same. They all use the scikit-learn library. I mean, you all use the scikit-learn library in your projects as well. It's all the same, like .fit, .predict functions. So coding them out are the same. The way that they work under the hood, slightly different. And for your project, you will be using a bunch of these algorithms. And what I will say is the algorithm that you choose to be the best one, perhaps that's the one that you take a deep dive in and understand more. So that's kind of like what the Mod 3 outlook looks like. Questions about that?
So is this more about understanding? So now we had a bunch of figures that came up whenever we ran the model.
Mm-hmm.
Understanding each part of that, will this section involve that?
So the thing that was slightly different about linear regression is that linear regression was a linear model that you have to fulfill a bunch of assumptions. And also linear regression is built off of a bunch of t-tests and hypothesis tests on each coefficient. That's how we talked about breaking all those numbers down. Good news is for most of these models, that doesn't matter. Most of these models actually deal with that for us. Something that I don't think I mentioned yet, all of these models are classification models. And I'll get more into that when we get there. But that is what the rest of these models are. So slightly different from regression models where we were predicting a continuous variable. These are classifying things, whether they, like, for example, I think if you want to take a look at the project, there are 4 different options for the project this time. Examples like, all right, is this, the one I remember is very morbid, but is a cancer tumor malignant or benign? Is it cancerous or not cancerous? I think there's another data set that you can choose from. Is it credit card fraud? Is this a fraudulent claim or is it not a fraudulent claim? So those are the kind of models that we'll be dealing with for this mod. Something else I forgot to mention, object-oriented programming, which is section 21. I'm skipping over for now, only because I think it's kind of random. I will be using one of the office hours to talk about section 21 instead, just because it's not super relevant to the material, but it's something that is kind of good to know, but not relevant to any of these sections for this mod. Questions about that? Cool. So that's everything I had to say about the mod. I do have a couple other like scheduling announcements, but I'll leave that till the end of study group. So cool. We're gonna start with linear algebra. Before we get started, and does anyone, again, final call for questions. Does anyone have any questions on material? I don't know if anyone started looking at it yet. Does anyone have anything in particular that they want me to talk about? All right, then let's get started. Linear algebra, I think I said as part of my stand-up, one of my favorite parts of math. So I'm really excited to talk about this. In this notebook, I'm going to go through why linear algebra. We're going to talk about the data types that we use for linear algebra. And these are actually just Numpy data types. We actually talked about, I had the exact same code back when we were talking about Numpy, like in mod 1. So this will be a bit of a refresher for that. We're going to talk about operations on vectors and matrices, how like addition, subtraction, broadcasting, which should sound familiar from Numpy, multiplication, division on vectors and matrices. We're then going to talk about systems of linear equations. And then finally, we're going to put it all together, looking at how linear regression works using linear algebra. I'm going to preface this entire study group by saying that if you don't understand any of this math that's going on, honestly, it doesn't really matter too much. You can still get a job in data science and not understand all of these like matrix things that we're dealing with. It's just something that's good to know because it is what machine learning is built off of. So worthwhile, like at least listening, and like at least some of these terms won't be completely foreign if you ever encounter them. So I do want to preface this study group by saying that.
So will the project be more focused on machine learning this time, or it's like an extension to this last project which we have done?
So this next project is going to be machine learning, and actually linear regression is a form of machine learning as well. We'll talk about that tomorrow, how machine learning works with regression. Not tomorrow, Thursday in Thursday study group. But yeah, we were already doing machine learning with the last project. And I'll talk about why that's the case. So it's actually going to be a very, very similar project structure. A bit less of like the iterative modeling within one single model, but instead of doing different linear regressions or different kinds of like one model, you'll actually just be testing all sorts of different models. So it'll be a little bit less tedious because you're not just like fiddling with one model. You'll be actually fitting 3 to 4 or more different models.
And this will involve pulling up data from in the web and then working on it.
Very similar. You're actually provided with 4 data sets that you can actually choose from. And you are definitely allowed to choose your own data set if you want, but you just have to get that approved by me first.
Okay.
Awesome. Anything else? All right, so to start, why linear algebra? I mean, I think I mentioned linear algebra is the basis of machine learning. It's the basis of many machine learning models. A couple in particular, as we talk about them, I'll be bringing back some of these concepts. But again, like it's not important to understand the math behind every model. So why linear algebra? Well, data is already set up into a matrix by default. We talked about matrices when we're dealing with Numpy. Matrix is any two-dimensional array. Any two-dimensional array is a matrix. So here, you have your rows and your columns. Technically, this could be considered a matrix as well. Linear algebra can also be used to model complicated things like language. Next mod, in mod 4, we'll actually be talking about natural language processing, and you'll see that words can be vectorized in a way that, I think this will make more sense when we get there, but the direction you go from king to queen is the same direction you go from man to woman. All of these like meaning behind words can be vectorized and have been vectorized, and we can actually make use of that in our modeling in the future. Linear algebra is also important for image compression and recognition. Another topic in mod 4 is image data and classification of images and object detection. Images are presented as tensors. And again, if we don't remember what tensors are, we'll talk about it in a little bit. But in an image, every single pixel is represented by a number. And the number represents the intensity of color in that pixel. In a black and white image, it's just a single matrix. But in a color image, you actually have 3 or 4 different matrices, one for red, one for green, one for blue, and different intensities in each one. And that actually comprises your image. So when we get to image data, we'll dissect that a little more and see what those look like.
One quick question. Now, is this the way all the barcodes and other things are read?
Barcodes, I'm not too sure. Images, I'm sure, but barcodes, I'm not sure if there's a different way that barcodes are read. QR codes are also read slightly differently, but I don't know how those work. But yeah, that's a good like comparison. But I'm actually not 100% sure how those are read.
Okay.
But thanks for that question. One of my favorite applications of data science and machine learning is actually in recommendation engines. One of my all-time favorite parts of data science. And recommendation engines are actually able to make very sophisticated recommendations by using linear algebra. When we get to that, I'll actually talk about the algorithm that Netflix uses to make their recommendations, and it does use a combination of matrix multiplication and gradient descent, which is very, very, very interesting. I'll geek out about that next mod. And finally, I don't know if anyone's familiar with this meme, but I just thought this was really funny because this is literally what we did. We did a linear regression project literally last week. And this is what we're doing. You know, we're like skipping over the intense statistics theory. We're skipping over linear algebra and skipping over multivariate calculus, all of which do make up linear regression. But all we did was do import linear regression. And we ran that model without really understanding how the model fits and how it works. So I just thought that was funny. Really quickly, just this part is going to be a little bit of a recap. Data types for linear algebra. This is another funny photo that I found. We have scalars, vectors, matrices, and tensors. And these are all different kinds of Numpy arrays, or just different dimensions of numbers. So a scalar is only a magnitude. Any number, if you just have a plain old number, it's a scalar. One level up from that is a vector. A vector is an array with magnitude and direction. And we'll talk about what that means like graphically in a little bit. But the coordinates of a vector represent where the tip of the vector would be if you traveled from the origin, and the magnitude of the vector would be its length in space. Again, we'll talk about this graphically later on. So a vector is really just like a list of numbers. A list of numbers is considered a vector. Next we have matrices, and as I've mentioned, matrices you have rows and columns, anything that is two-dimensional. They can be interpreted in different ways in different contexts, but often used to represent multiple simultaneous vectors. And I could talk about that later on when we talk about linear regression using linear algebra. So vectors and matrices can be multiplied by a scalar to create a change in scale or direction. And then finally, tensors are multiple matrices. So like with the image example I was talking about where you have matrix, 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 one for red, green, and blue, those are tensors. This is the exact code that we had back in like section 4 when we talked about NumPy for the very first time. This is a vector, one-dimensional, so you can see it in the shape you only have one number. This is a matrix, two-dimensional, so two numbers in your shape, and tensor is 3. I'm not going to go too much into this, but you can index things differently. So for example, this tensor is two groups of two. We can mess around with indexing it just to see what result we get. This is something you can definitely play around with. Next thing to know is the magnitude of a vector. So this list of numbers we can also interpret in linear algebra context as a vector. 1, 2, 3, 4, 5, 6 basically means that we have 6 dimensions, and for each dimension we have a number. So in the first dimension you're going up 1, second dimension we're going up 2. Let me use a smaller example to make sense of this, but the magnitude of the vector basically tells you the length of it. So here, thank goodness, we have this built-in method, np.linealg.norm, and you can find the length of the vector. I want to quickly draw a diagram to show you what a vector looks like graphically. So imagine we have 2 dimensions. Let's just go with 2 dimensions for now. Let's draw these little arrows over here. And let's just say we have the vector 2, 3. So vector 2, 3, what that means that is in, and these can just be 2 dimensions. Here, I'll just call this x1, x2. And so 2, 3 basically means that this vector is going 2 in one direction, and then 3 in another direction. And so you see in this 2-dimensional space, this vector actually looks like this. And let me draw this line over here. So this vector, and vectors have a direction. A vector is moving that way. And so given this 2, 3 vector, 2, 3 sort of tells it the direction you're going, but you also can have the length of this vector. So because it goes 2 in this way, 3 in this way, you actually sort of solve it using the Pythagoras Theorem, which is what this formula is. So if we actually do np.linealgebra.norm of 2, 3, let's see. Oops, no, that's already there. I meant to do np.array, and we want to do 2, 3. I think that comes up to like 4 something. Oh, 3 something. So 3.6 is the length of the diagonal, also known as the magnitude of this vector. So if you ever see like magnitude of a vector, that's what that means. Questions on this part? Vectors can also go negative. So if you ever see like 2, -3, -3, let's see, if this was -3, all that would mean is instead of going up this way, it actually goes down that way. Just so you know. And of course, this can be expanded into many, many dimensions. Of course, we can only see up to 3, but the concept does scale to higher dimensions.
One quick question. Now, you were talking about Pythagoras theorem. So the np.lineage is the Pythagoras theorem, or?
Yeah, it pretty much does the Pythagoras theorem. And it also does the Pythagoras theorem if you have more dimensions, because Pythagoras theorem is just used for like triangles, or just like 2Ds. But yeah, np.linealgebra.norm will do it for multiple dimensions. All right, something else that's good to know is transposing. I think we might have seen this if anyone has ever needed to do this with a data frame. Transposing a matrix just reverses shape order. More specifically, if we have a matrix that looks like 1, 2, 3, 4, 5, 6 like this, it just sort of flips it along its diagonal, makes the rows into columns, columns into rows. So instead of going across 1, 2, 3, 1, 2, 3 after you call transpose, 1, 2, 3 goes downwards instead of across.
The same as Excel.
Yes, exactly. Same as Excel. You can also transpose a tensor, although that is very, very rarely done. But I think it's also useful to know that what you're doing when you transpose a tensor, you're just flipping the shape order. So this tensor that we started with, that goes like 1 through to 24, has the shape 2, 4, 3. When you transpose that, it does look a little bit crazy because all the numbers are like split up in weird ways. But all you have to know is it reverses the shape order. How this works, not important to know.
So in the function, what is the easiest way to remember whether the row comes first or the column comes first, or is there anything?
I sort of like to think like small to big. I know that this way of thinking doesn't work for everybody. I have like heard from students that like that doesn't make sense, but the way I remember it is you start by counting the smaller things. So in this case, you have 2 rows, and because the smallest one is row, like the most nested in list is the row, and so because of that, we have 2 rows, and each row has 3 items. So in this case, the smallest item that we have is, let me see if that makes sense. Here we have 3, let me see. No, that doesn't make sense. I guess for a tensor, it's a little bit different to think about. For matrices, it's always rows then columns. For tensors, it's like number of matrices and then number of rows and then number of elements in each row. I think that's an easier way to put it. Yeah. I guess so small to big, big to small. So here you can think about number of rows and then number of elements in each row. Maybe that helps. Yeah, I think I misremembered it earlier on. But yeah, questions about transposing. Cool. So with vectors and matrices, we can actually do operations, like mathematical operations. The easiest one to think about is addition and subtraction. So just so you know, in case you come across this kind of notation, you can also denote a vector by having the numbers stacked like that. So vectors can also sometimes look like this. So in this example, if I have two vectors and I want to like add them together, all you have to do is do the addition or subtraction element-wise. And element-wise, by that what I mean is, let's say we have v is 2, 4, w is 3, 2. All we have to do is add element-wise. So if we take a look at v plus w, it's 5, 6, because 5 because we're adding the 2 and 3 here, and 6 because we're adding the 4 and 2 there. If we're doing v minus w, exactly the same thing. And remember, vectors can go negative. So in this case, we do 2 minus 3, which is -1, 4 minus 2, which is 2. So this is element-wise addition or subtraction. Questions about that?
One thing I was facing the issue with plotting, right? When I was, whenever there was negative numbers, right? The one thing it was like getting into the infinite loop, right? What happens with this?
That's possibly when you're log transforming. Yeah, so log transforming is something very specific. You just cannot take the log of a negative number. So usually if you're taking the log of something that has a negative number, you want to scale it first and then take the log of that. So you can actually do like a min-max scale or something like that that will bring the numbers between 0 and 1. And then that just makes sure that all the numbers are positive, and then you do a log transform. So that's something that you can do. Yeah.
I mean, specifically, I faced the issue when because the longitude had a lot of negative values. So it was really not allowing me to write that at all. So now I'm told about this what do you say? What was this? Here in vector, and if we are plotting, will we face the same issue?
Oh, plotting will be fine. Anything with plotting will be fine. Like if you didn't take the log of like the longitude and latitude, you still would be able to plot it. The only reason why you couldn't be plotted is because of the infinity numbers. So this, when you're plotting, this shouldn't be an issue. Yeah. One thing I did want to talk about was like what the addition of vectors means, like graphically. So really quickly, I wanted to draw a diagram. I didn't charge my tablet, so we have to do this. So all right, we have our x1 and x2. So the first one, let's actually take a look at graphically, what does v plus w look like? So here we have v, and v is 2, 4. So let's say that this is 2, 4. Let's say v is like this. And this is 2, oops. This is 2, and this is 4. Now when you're adding a vector, when you add, I sort of like to think about it as like, okay, joining the vectors to each other. So from 2, 4, let's add on 3, 2. So what I mean by that is, all right, here we have 2. Let's add on another line that is 3, 2. So one way to think of it is, all right, from here, let's move right down this line 3 steps. And so, and yeah, let's move right 3 steps, and then let's move up 2 steps. So right about here, we connect this line. And so this second part is the 3, 2. So here you can see we have 2 vectors stacked on top of each other. And the result of the addition is, and let me use a different color real quick. The result of this addition is this green line here. This green line over here that actually, if we were to do the numbers, let me get into this text. This, you see we're adding 3 here and we're adding 2 here. This results in 5 and this results in 6. That's how we get to this number, or this resulting vector being 5, 6. So graphically, that's what is going on behind the scenes. Again, not super important to understand this part, but I think it's, you know, good to know, and it does help some people understand. Questions about this?
I have a question.
Mm-hmm.
So 2 things, I guess. First, you always start at 0, 0 when you're talking about vectors?
Yes. So vectors, I mean, you're kind of like doing it relative, and if there's nothing to do it relative to, you do start at 0, 0. Because vectors are more so than like on from a specific point, it's more representing like a direction and also like some sort of magnitude. But in case of like in this specific example, when like, you know, I didn't specify any other starting point, yeah, we start at 0, 0. And because like this, like for example, this second one, when I wanted to add on this W vector, I started not from 0, 0, but I started from where that ended. Mm-hmm.
And so is the major difference between a vector and a line that a vector has a direction?
Yeah, the vector does have a specific direction that can be like represented in like numerical space.
Okay.
Awesome, thanks for those questions. All right, this next part again is going to be kind of review because I believe this exact code is in my other notebook too, but broadcasting. So if you don't remember, NumPy arrays, why arrays are more powerful than lists is they allow for broadcasting, which happens when you perform operations across arrays with different number of dimensions. Basically, you can do broadcasting as long as the higher dimension array contains the same shape. So here, very briefly, we have this scalar 4 that we're going to broadcast onto this vector. And remember, if we do vector plus scalar, what it does is we have this vector 1, 2, 3, 4, 5, 6. We're broadcasting the addition of 4 onto every element in the vector. And so I think vector and scalar is probably the most common usage of broadcasting. Data frames actually make use of broadcasting as well, which is why, you know, you're able to do entire row, entire column operations just by doing like, you know, column like plus 10, you'll add 10 to everything in the column is because it's broadcasting. Very similarly, you can also broadcast vectors onto matrices. This example will not run because I wanted people to type it out. But for example, if we had the vector 1, 0, 1, and we have this matrix of 1, 2, 3, 4, 5, 6, we can broadcast 1, 0, 1 because it has the shape 3 onto the other 3 element subarrays within the matrix. So we do matrix 1 minus vector 1. Each 3 element row will have minus 1, 0, 1. And that's just, I mean, using vector matrix broadcasting, not as common, but in case you have to do it, just know that that is an ability. And then with Tensor 2, with tensors, basically you can also broadcast things onto tensors. And with tensors, you can broadcast matrices. Like if you happen to have like a matrix of this shape, you can broadcast that onto the tensor. Similarly, you also be able to broadcast any 3 element array. And then similarly, any scalar you can broadcast onto a tensor. So just good to know, broadcasting is super powerful. It's basically, whereas in a Python list, you would have to loop through everything in the list or like use a lambda, and lambda is really just looping as well. An array just does it all at once at the same time, much faster. questions about that? Cool. These are just like superpowers of NumPy. All right, next we're gonna talk about multiplication. With matrices, there are different kinds of multiplication. There is the Hadamard product, dot product, and cross product. The main one we're gonna be using is actually just the dot product, but very quickly I wanted to talk about what these other ones were. So here, Hadamard product is very similar to what we were doing before, element-wise multiplication. Actually not used very, very often in linear algebra, but just to know, if you want to do the multiplication of two arrays with a Hadamard product, first you have to do numpy.array, and all you would have to do is use the multiplication symbol, and that will work. So numpy.array, there we go, and that multiplies it element-wise. So you can see like 1 times 3, which is 3, 2 times 4, which is 8, 1 times 5, and then 2 times 9. So this is just element-wise multiplication, similar to what we were doing before with addition.
One quick question: do we have to import these things, or like an inbuilt thing with NP?
Yes, for this you just have to import NumPy. Yeah, you just have to import NumPy, and I had it imported up here. Yeah.
You defined every. I mean, you had variable for each one of them, right?
For these?
Yeah.
Nope. These are just arrays that I'm defining right here.
Okay.
Yeah, I could alternatively do like A equals to this. I could also do B equals to this, and then do A times B, same thing. But yeah, I could also plug this straight into A and B. I don't need to define A and B, and it'll work the same way.
Okay, it's the same thing for, and like just the way of multiplication will change with dot product and
That's
add.
right. Yep, they're just different ways of multiplying.
So instead of just a star, maybe something else it will be. Yep,
that's right. So using the star, which is the default for doing multiplication, if you just use the star, it will do this kind of multiplication. Any other questions about this? All right, so for matrices, the one that's actually used more often is the dot product. And the dot product is a little bit confusing because it's not exactly element-wise, and it doesn't really have like a rhyme or reason why. But this is the most commonly used kind of multiplication when you're doing linear algebra with matrices. So how this works is you're actually taking the rows of the first matrix, and you're doing an element-wise multiplication with the columns of the second matrix. So as you can see here, we're actually going to do element-wise multiplication with this first row here of A11, A12, multiply it with B11, B21. The way I sort of like to think about it is here in this first slot, what intersects is the first row and the first column, so that's what I'm going to multiply. And then you're actually doing an element-wise multiplication within that. So you can see here, we're multiplying A11 times B11, so these two. Actually, let me circle it so it'll be a bit clearer. So we have this row, this column. And so we're doing A11 times B11 plus A12 plus B21. So we're actually taking the product of the first one plus the product of the second one. And that creates this one number. And then you have to repeat it for the rest of the rows and the rest of the columns. And you only look at rows for the first matrix, and you only look at columns for the second matrix. I will say, if this is confusing, don't worry, because we actually have built in a NumPy dot product formula.
Yeah. So, here, so let's say in a data frame, like when we have like the rows and columns, like if we have to multiply, so I mean, if we just have to multiply each item by item, then this dot product will work, correct?
If you want to do item by item, and if it's in a data frame, honestly, you would actually probably end up doing this the Hadamard product first, because
Hmm.
dot product is used for very specific things, and it's for very specific linear algebra things. For example, like I'll talk about it later on, but if you're just, you know, working with a data frame and cleaning your data and transforming your data, very likely it will be Hadamard product. Because when you're, you know, transforming your data frame, you're not really doing linear algebra things. That makes sense. So you will really only do like this dot product specifically if you're doing specific linear algebra operations, which honestly in our course past this study group, we're not going to do much of.
Okay.
Yeah. So honestly, not much to worry about, which is what I prefaced this with. So, all right. So because we're taking the rows multiplied by the columns of the second matrix, with this rule, there are some shape restrictions to doing matrix multiplications, meaning that you cannot just multiply any two matrices together. They actually do have to have some commonalities in their shape. And because these examples are squares, not as clear to see, but I'm actually going to clear these circles for a while and talk about any matrix A and B where you have dimensions m times n and p times q. So I'm actually just going to use squares to represent matrices. So really quickly, let's say I have this, let me see, where should I draw it? Okay, let's say I have this first matrix that is this red rectangle. And this red rectangle matrix has m rows and n columns. My second matrix, I have, oops, that is not what I meant to do. My next matrix, I have shaped like this. I have, let's see, p rows and q columns. So because the way that we're doing multiplication is that we are going to multiply, you know, row by row. We're going to multiply it by column times column. What number of elements has to match? Does anyone have any idea? Like something has to match here. I don't know if I set that up very clearly.
NNP?
Yeah. So not exactly NNP. I know it's like with this notation is a bit confusing, but the number of elements in each row. Oh, actually, yeah, you're right. NNP, yes. NNP have to match. So basically the number of columns in the first matrix has to match the number of rows in the second matrix. Just because, oh, let's see if this works. Because we're doing 1, 2, 3 elements here. We're doing this element-wise multiplication with 1, 2, 3 elements over here. So yes, thanks, Henry. N and P have to match. Usually, when I'm thinking about it, I like to think about if you put the two dimensions of the two matrices side by side, the way I remember is like the inner two numbers have to match. So yeah, in this case, N and P have to match. But different people remember it different ways. I will say this specific question of like, if you have an M by N and P by Q matrix, I've actually gotten this question once in an interview. It was like the only linear algebra question I've ever gotten in any interview, just so y'all know. But the fact that it has come up once, useful to know. This is definitely something that I would like come back to after graduation to like study. And so with this dot product, very simple. You have numpy dot dot. All you have to do is feed it in A and B, and it will do that multiplication for you. Really quickly, the order that you do your matrix multiplications actually matters. And so if you see this is A dot B, if I were to do it the other way around and do BA, it results in different numbers. So that's just something to remember. The order in which you do your matrix multiplication does make a difference. And this is just another rule. If you're doing multiple things, yeah, the order matters. If you were to do like this first two first is different from doing these last two first. And of course, A, B, and C are all different matrices. Questions about that? All right. I also have cross product. Cross product, not important for us at all. But just to quickly go through, cross product is used for more abstract applications of linear algebra, and we'll just define it, what it means for vectors. A cross product has this formula. And basically, you have a bunch of vectors. N is a unit vector that's perpendicular to the plane formed by two vectors. So for example, if A and B are two vectors that are, let me see if I can try and draw a 3D space on here. So let's say I have this 3D space here. This is the third dimension. And let's say this is our first dimension, this is our second dimension. If I have two vectors, and I'm just gonna have them randomly placed like here, going this direction, and another one going here in this second direction. If you have these vectors, you can technically form like a plane. So imagine you're filling up all the space that this vector takes up. So these two vectors are like lying on the ground, and the space that it takes up, that's the plane of your vector, formed by the two vectors. And then N is a unit vector perpendicular to the plane formed by two vectors. What that means is a unit vector that is perpendicular to a plane. Imagine a unit vector, and a unit vector basically means a vector with a length of 1 that is shooting upwards. That is shooting upwards from this plane. That's what that means. I know it's kind of abstract, but that's what it is. It has a length. This cross product has the length of a length equal to the area of a parallelogram formed by these two vectors. And I feel like I have to explain a lot of things here, but the parallelogram formed by two vectors is, if you imagine, like if we have this vector here is a copy of the blue line, this vector here is a copy of the green line, this parallelogram has an area, and it's going to be equivalent to the length of this vector. And when you do a cross product, you lose a dimension, which is why from that, you have a line that shoots out. I know that doesn't make sense. If it doesn't, and it honestly really doesn't matter for our purposes, but it is still in some of the linear algebra readings, so felt like I should mention just in case. All right, so from that, we're going to move on to division, which is not possible. You cannot divide matrices. It's just not something that exists. Instead, we have inverses. You can inverse a matrix. So not exactly division, but similar. It is not possible to divide matrices, although you can actually still broadcast element-wise. So if you did have like a vector or a matrix and you divide it by a single number, element-wise is fine. But if you have two matrices, you cannot divide one matrix by another matrix. What we can do is find the inverse of a matrix. So the definition of an inverse of a matrix is that if you have the matrix and you multiply it by its inverse, it should give you the identity matrix. And the identity matrix is the linear algebra version of the number 1. What the identity matrix looks like, and it can go in many, as wide as needed. Identity matrices are basically any square matrix that has ones across its diagonal. And mathematically, it works just like the number 1. If you take any matrix multiplied by an identity matrix, you get the matrix itself. So the inverse of a matrix is given by, is a matrix that will result in the identity matrix when multiplied by itself. So this equation always holds true. And also for a matrix and its inverse, the order doesn't matter. So for inverse, for matrices and their inverses, when you multiply them out, they on both sides will result in the identity matrix. Questions about this? All right. Also, just so you all are aware, all of this material is taught maybe over like 5-6 weeks in a college class. So if this is a lot of information, it's okay. It really is a lot of information. So this is showing the effect of matrix multiplication with an identity matrix. So here I have X identity matrix and the dot product. So here you can see I have this array, this matrix, sorry, of like just random numbers that I plugged in. I have this identity matrix that Numpy actually has a really nice identity function that creates this identity matrix. And when I multiply them together, when I take the dot product of them, you result in the same numbers. So that's just showing the result of that. And also something else to show, we'll get to that later. X was this was X. You can get the inverse of a matrix using Numpy as well by linear_inverse.x. So this happens to be the inverse of that matrix. Numbers are complicated. There are formulas to do it by hand, but we don't need to know those. And if you were to take the dot product of X and its inverse, you get the identity matrix. There's a bit of rounding here, but pretty much the identity matrix. Questions about this? All right, really quickly, I didn't realize how much time has passed. We're gonna talk about systems of linear equations, and that's gonna lead us into our linear regression example. So very, very quickly, what are linear equations? All the results of our linear regression models are linear equations, because remember, we were talking about coefficients, and the way that you set up your formula for predicting price, those are linear equations. So linear equations only have linear variables. So that means our unknowns, our x's, are only multiplied by a scalar and raised to a power of 1. So for example, this is a linear equation because you know, your x is not raised, is only multiplied by scalars. This example also linear because pi is actually a constant number. E is also a constant number. These are not linear equations because here you can see it's x squared, and once it's squared, not linear. You have a log here, not linear. You have all sorts of funky stuff. All of that, not linear. So we can solve systems of linear equations with linear algebra really easily. And this will actually lead us into our linear regression example. So here we have two equations of using x and y. And we basically, from this system of equations, want to find what x and y are. If you've taken like an algebra class, you would just like substitute x and then mess with the formulas a little bit to get like a y, and then resubstitute and solve for x and y. But we can actually also do this with linear algebra. First thing we actually need to do is represent this as matrices and vectors. So here what we have is x minus 2y, 3x plus 2y. We actually represent here as like 1, negative 2, because minus 2y, 3 and 2, because 3 and 2 over here, multiplied by the vector x and y. And if you were to do the matrix multiplication for this, it actually does work out and give you this equation. And we again represent this as its own vector. From that, it does require a little bit of math work, but, and actually let me output this first. So we have A and B. We're gonna call this left side one, let me circle it so it's clearer. We're gonna call this one A, this one B, and we basically wanna find what x and y are. So from here, we start with this equation here. We start with A dot product x equals to B. That is exactly what we were given here. From that, how we start solving for x is, if we remember in algebra, if we want to solve for x, we want to like have it by itself on one side of the equation. What we can first do is we can make use of what we know about the identity matrix. So let me scroll down a little bit. What we know about the identity matrix is that if we were to multiply the inverse of A over here, oops. If we were to multiply the inverse of A, this becomes 1, which is basically like multiplied by x, so it becomes nothing. But when we multiply it by the inverse of A on one side, we got to do it on the other side as well. And then if we just work through the equations like this, we end up with x being equal to the inverse of A multiplied by B. One last thing to note about this is that we're doing the inverse of A to the left of everything that's existing, which is why here we don't just put B dot A inverse, we have A inverse dot B, because the order matters. If we're doing this to the left of everything, this has to go to the left of everything. And so that just works out. And if we were to do this, we end up with, we want to find X. All we have to do is evaluate A inverse dot product B, which very nicely we have here. A, B, we have inverse A dot product B. Once we do that, we end up with, and let me clear these drawings, we end up with X being equal to 3, Y being equal to 1. And if we were to plug these back in, it makes sense, because if X is 3, Y is 1, so it's just minus 2, we end up with 1. Here, 3X is 9, plus 2Y gives you 11. So that's one way to solve system of linear equations. If you have like more equations and more unknown numbers, you can solve it this way too. Hopefully we can do this in the last 5 minutes. But we're going to talk about how this works into linear regression, which I think is actually one of the most elegant math things that exists. So what we're going to start with, we're going to use that car data frame that we used. And hopefully we have that here. Here we go. This car data frame I think we're pretty familiar with. And what we want to do is, for this linear regression example, we're going to predict miles per gallon. So here what I'm doing is I'm doing the same thing. I have my X and I have my Y. So here are all of my features that I'm going to use for my linear regression. And what we're going to do is we're going to solve this. We're going to try and solve our linear regression using this method. So really quickly, we have to give it an intercept term because I won't go into why, but there is a reading and I'll send that out as to why we need this intercept term. And then let's take a look at our X again. We have this constant term here just because we need a coefficient for the intercept. So the equation that we currently have is we have Y equals to X multiplied by B. And actually, let me draw that out so it's a little bit clearer. And apologies, I think we're going to go a little bit over time. We have our Y data, and our Y data is just like one column of data, right? Our Y data is equal to X, and X is all of our X columns. Oops, that's not what I meant to do. Let's do that. I want a square is equal to X multiplied by B. And B is going to be a single row that matches the number of columns in X. So let me just draw this a little more clear. This is X, this is B. If we multiply it out, it'll make sense, and this is Y. And we basically want to find our coefficients. B is going to be our coefficient. So we want to solve this equation. And so if we want to solve for B, using the same thing that we did before, we want to multiply it by, we want to multiply both sides by the inverse of X to get rid of X on this side so that we can get B by itself. So here I have the inverse of X. And you can actually find the inverse of a data frame as well. So you can plug in data frames and it'll recognize data frames as matrices, which is really nice. So when we do this, we unfortunately run into an error that's saying that the last 2 dimensions of an array must be square. Basically, that is because you can only find the inverse of a square matrix. And if you think about it, it has to do with like, the dimensions that have to match when you're doing the matrix multiplication process. So let's move past that. And with some linear algebra theory, we are going to have to figure out a way to get rid of this X without without needing to find the inverse of X. So the method that we use, and if we remember this from earlier, we have to use the transpose. We don't really have time to get too much into it, but if you multiply X by transpose of X, so let's just imagine we have, this is X, this is the transpose of X. The resulting matrix will be a square. This is something that I did not mention earlier, but if we had a matrix that has the dimensions let's see, let's do M by N, P by Q. We already said that N and P have to match. That's one thing. The other thing is that your resulting matrix, the product of multiplying your matrices together, is going to have the shape M times Q. Which, because, you know, this is the transpose of this, if we were to multiply the transpose by the matrix itself, you end up with a square matrix. Definitely take some time to digest that whenever. But that's what we're going to use. We're going to use a transpose. So how that works, I'm actually going to walk through the whole derivation process. We start off first with y equals to x times b. So from that, we were like, okay, we can't multiply it by the inverse because the inverse of x doesn't exist. We're going to do transpose first. So first we're going to start with, all right, let's left multiply x transpose on both sides. So here we have x transpose there. And so that's still equivalent. Now, this product here of x transpose x, now that is a square matrix, and that's what we can use to isolate B. And so in a kind of confusing way, we're going to take the inverse of x transpose x. So we're actually going to do this. So once we do this, sorry, this is not very clear. Once we have this, let me draw it on this side too, really quick as possible. X transpose y. There we go. Once we have this, I hope that made sense. This and this will cancel out and isolate B on this side. And then this is all we have to evaluate, which is what I have here. X transpose x, whole thing inversed, multiplied by x transpose y. So really quickly, I did all the math out here using the Numpy formulas. B gives you these coefficients for your linear algebra. So actually, let's take a look at what that looks like. I zipped together the name of the columns with the coefficients. So these are the coefficients. What I'm going to do now is let's quickly compare these coefficients with that we got from our circular linear model. So if I quickly fit that, you can see here now that these coefficients match these coefficients. Takes time to look at it, but point I'm getting is you can actually solve linear equation using matrix multiplication. So yeah, that is all I had. These additional resources, especially this first playlist, is by the YouTube channel 3 Blue 1 Brown. It's like a historically known, very, very good playlist for linear algebra. Highly recommend that, like, you know, when you're preparing for interviews in the future, to just like go through all of those videos. They're like the stat quest for linear algebra, in my opinion. So that's a really good resource to remember. And I have linked some other things about some additional reading if you're interested. But yeah, any questions? I know there's a lot of information with this study group, but any questions?
So I mean, there are more video materials where, like, okay, each terms are explained properly.
Yes, 3 Blue 1 Brown. If you go to their, let's see, I think if you like Google them, they have, let's see, yeah, linear algebra is their most popular one. And their playlist has a bunch of videos explaining like everything. So here you can see like, all right, what does they break down what matrix multiplication looks like. They go way more in depth than we need to. They actually talk about cross products if you're actually interested what that was. And they go, yeah, really, really in depth. But I think for us, more important to just look at like, all right, what is like the graphical representation of a vector. I would say, yeah, I would say more the first half of this is more important. But it does go into a lot of theory, which is not super necessary. I think for us, what's important to know is that with linear algebra, you can work across multiple dimensions, and also the fact that you can represent, you know, our feature space as a matrix as well. But cool, hopefully that wasn't too overwhelming. I love this stuff, but I also spent like multiple semesters of college on it. So I recognize that is a lot of material. Like we covered like half of a college semester in literally 1 hour. If there are any questions, if any of you are interested, do let me know. But I also do recognize this is one of the less important sections to understand at this point.
What about the group you were talking about? You said 4 groups.
Yeah. So that I will send out the groups. I do sort of know like your working schedules and your time zones. So I'm actually going to arrange it that way so that, you know, you're at least communicating with people like within your similar time zones. So I'm going to do that, and I'll send out, I'm going to send out like the groupings, and I'm also going to have one person in each group in charge of making this DM.
So this will be like the same group will work for the project as well?
For the project, I again will give the option of working in pairs or individual. But if it is in pairs, if multiple people in a group opt to do pairs, then I will group you guys together. Yeah. I will say that like my other cohort, I do recognize that they are a full-time cohort, so they do have more time to work together, but their experience with these working groups has been great because, you know, you get to bounce ideas off of each other instead of just me. So I think it's going to be a good benefit. Oh, I did have one final announcement, but I understand if anyone has to leave. My one final announcement is that I will actually be out of office for the week leading up to Thanksgiving. So for those sessions, they're all going to be covered by other instructors. I've already gotten other instructors to cover every single study group that we have. And because I won't be able to do office hours, there will be an additional open office hour. I believe there's one the week before Thanksgiving and one the week of Thanksgiving, because I will also be out that week. There will be open office hours conducted by other instructors. So if any of you know, James is going to cover a couple sessions. James is going to cover some. Abinit, if anyone's met him before, Abinit's going to cover a couple. Lindsay, who's another one, will cover a couple. Raphael's also going to cover one of our study groups. So you're all going to be taken care of. So no worries for the 1.5 weeks that I'm out. And this is going to be the week before Thanksgiving and the week of Thanksgiving. Just to let you guys know that. But
do we have office hours in those weeks? I mean, this is just...
Typically no, but because I won't be around to give one-on-ones, there'll be an open office hour to just ask any questions that you have during those times. As we get closer in next week, I will say this again, and I'll also post a message in Slack, just so that it'll all be clear for you all. But just wanted to let y'all know sooner rather than later, just in case. One final thing. Next Wednesday is also off because it's Veterans Day, and Flatiron School is off for Veterans Day. Just a reminder for any of you that have Wednesday one-on-ones, feel free to just pick another slot for that week. So cool. I know this was way over time, but any last questions? All right, if there's anything else, please feel free to Slack me about anything. I will see you all again on Thursday to talk about calculus, and also at your one-on-ones this week. All right, have a good night, everybody. Bye.